All right, buckle up for the last review. This is going to cover a bunch of the details for things. Um, there's going to be stuff even earlier than this, but we're going to focus on this. You need to know stuff going all the way back to the very beginning, getting into crystal planes and the crystalline behaviors of the material. Based on those fundamentals and the concepts of slip planes and slip systems, deformations in metals, these are really important. Really having a clear picture of what is stress and strain, all of those sorts of details. All of this becomes critically important for all the reasons. Understanding what the tension is on a material. Where is the tension? Is it in two axes? Is it in all axes? Understanding what strain is, meaning the change in shape of the material, and what we're doing with an extensometer in a tensile test to see what's happening. Understanding what is Young's modulus, being familiar with the concept of Poisson's ratio, in order to understand what some of the mechanical properties are. So the slope of the stress strain curve giving us some sort of an idea which is strongly bonded or weakly bonded, and how all of that works. The elastic properties of recovery and how things can twist. So the difference between a shear modulus and a bulk modulus, in terms of changes in geometry, understand how things scale relative to each other, metals, polymers, composites, all of those things. Understanding about linear elastic behaviors and what these deltas actually mean. Understanding clearly and being able to clearly articulate the difference between plastic and elastic deformation. Which one is which? What does it mean? What's storing energy? What's storing more energy? Tensile strength, relative comparison, and really a lot about the concepts of ductility, toughness, being this area under the curve, and resilience, to understand what a material can do, what kind of abuse it can take, the idea of unloading and elastic strain recovery, as well as hardness and surface properties. So again, this is one of the key chapters that covers all of this stuff, and there's so much important information. This is the kind of the baseline for everything. That's why I'm focusing here. Once you've done that, then you come up to the idea of these dislocations and these different kinds of bonds, and how these half planes of atoms cause a defect to move through, like that ripple in a rug moving through the material. So there's a slip and an edge dislocation that happens. And there's also, because you can't have plastic deformation without a slip system and without a plane being able to, that defect being able to slip through the material. Edge dislocation versus screw dislocation and why they are different. Understanding what a slip system is and how some of this works with the dislocation motion, and being able to identify how this behaves. So understanding that these happen at an angle. So polycrystalline materials, what's happening at these grain boundaries. We've talked about this at length. Isotropy versus anisotropy for cold worked versus material that has not been cold worked. So maybe one that's been freshly annealed or equiexed in some way. And the idea for some of these things where you have an anisotropy because you roll a material, then you cut out of that a slice, and it becomes non-circular when it has an impact. What these grain boundaries are in terms of how the propagation happens, coming up against those grain boundaries, what happens with impurities, creating the compression tension balance in the materials, even the alloying and things that we do to strengthen alloys, understanding why we would want to do that, especially based on the way that they can interrupt slip planes and slip systems such that they are stronger materials as a result. What do we do for cold working? How does that cooperate? Understanding that when two half plane dislocations reach each other going opposite directions, they undergo annihilation, meaning they cancel each other out and become a whole plane again. So mechanical properties change with cold working, so things change dimension. The grains get smaller, hardness changes in certain directions, tensile strength changes in certain directions. Then you heat treat and change that tensile strength and recover ductility. These always have that inverse relationship. And this gives us some of the properties for how heat treatment works and allows for diffusion to bring together and cause annihilation of these slip planes, especially given significant times in order to make those things happen. So recrystallization, really very important from large grains to smaller grains, improving hardness, then grain growth after longer times at those elevated temperatures. And depending on what you're trying to do, you change the temperature at which you're doing them to start recovering from the effects of the cold working. So we talked about how polymers do things a little bit differently very recently. The reduction in diameter, we need to understand how that works. And it's different for these different materials. As you do increased cold working, some of these things work harden and change significantly. Copper, not so much. The 1040 steel has a significant change in properties as a result of the cold working. So you can fine tune based on end application requirements what combination of steps is going to get you what you need. So hot working is above the recrystallization temperature, cold working is below. So even if it's a couple hundred degrees, it's still cold working. It's just below the recrystallization temperature for that specific material. So something like aluminum is going to have a much different cold working threshold than steel will. Grain sizes and influencing properties, small grains versus large grains. These are things that you guys need to have a really super clear handle on. Failure and the difference between ductile and brittle. You need to really crystallize this in your minds, have a very clear idea what a ductile versus brittle failure looks like, something that's in between. Something that has a large failure versus catastrophic failure, how this works. So these nucleation sites creating voids in the materials, different from polymers, but some commonalities in the mechanism, whether it makes a cup and cone or a brittle fracture, and why. The failure origination point, it's important to just understand what's happening with these materials, whether it's intergranular or it's transgranular going through the grains, to understand what's happening. So ideal versus real materials is important. Flaws and stress concentrators become really important because at the edges of a crack, your stress gets concentrated. And that's why we design stuff without sharp dimension transitions, because that gives us concentrated stress. Same force, smaller area, higher stress in that concentrated region, which promotes failure because that concentrates the force. And there's differences in how cracks propagate in those two different materials. So brittle is very sharp. A ductile is much less sharp. And the crack propagation just needs to be within a certain range of the elastic modulus. There's a specific surface energy and a half length of the internal crack, because you're looking at one side instead of double counting both sides. You want to be paying attention to that. So the fracture toughness of different materials, we need to understand kind of how that works relative to each other. Especially when we're looking at the crack growth and fracture design criteria, you want to make sure that you're below a certain threshold, and there's a couple different design evaluation mechanisms where we can balance this out and figure out which material size, spec, and dimension is going to give us what we need. Impact testing we do to understand the toughness of material, and it really, really helps to get a clear handle on how these things behave. Because when the temperature changes, there's a ductile to brittle temperature transition, and FCC metals are less prone to this. Iron and BCC metals are very susceptible to this. High strength metals are very low impact energy to begin with. But steel can be severely compromised, and this is why ships often end up sinking, is because of the behavior changes below that ductile transition temperature, which is different depending on the grade of the steel. So there's also fatigue, which happens when there's cyclic loading on the material, and there's an unsafe region and a safe region. For some materials, there's a fatigue limit where something won't fatigue for lots and lots of cycles, like a spring steel, for instance, has a threshold for fatigue that you can run it for a gazillion cycles, and for all intents and purposes, it really doesn't fatigue. Whereas if you put mild steel in that application, it would fatigue very quickly. So crack growth and propagation create all sorts of difficulties. We can change the surface by a few different mechanisms and change our design. We can do some other processes, carburizing and all sorts of things, changing surface materials, and that's how we do case hardening and all kinds of stuff. Creep is also another big issue, and that's why we dedicate kind of a whole at least a little bit of a section to this, because there's a steady state creep rate that happens that's different for different materials, so they move over the course of time under the loads that are given. Then we get back into stuff that's a little bit more recent, and we start looking at phases and equilibrium, understanding how these interact. So we went through a lot of this in some more detail for the review for 3, because this is super important stuff. So you need to understand the lever rule, you need to understand how to use it and how to read phase envelopes, phase diagrams, understand for a given system, whether it's for most part, we're going to be testing over things like binary systems. We're not going to go to trinary systems and be as mean as I could be, because then everybody would fail and there would be much wailing and gnashing of teeth. Really need to understand what microstructures are and how they look relative to different areas within a phase diagram. So this is literally, people get PhDs in this stuff, so you need to really sit down and study it, look through examples, all of those sorts of things. Understanding the terminology, eutectic, eutectoid, peritectic, all of these parameters are of key importance. Understanding when something is hypoeutectic, what does that mean? Hypoeutectoid, hypereutectoid, what does that mean? What are these different compositions? What are the weight fractions? What are those phase diagrams where do we read off of the phase diagram for those particular parts, and the effects of alloying conceptually. What does that mean in terms of the changes to the material, and how do those come into play? Because there's just so much that goes into this. So I'm not going to go into as much depth since there is another review video on those topics. Nucleation is really important because this is about the growth and rate of change of phases. So grain growth is governed by all of this. These phase changes of all of these materials are important, especially because of the recrystallization, the effect of temperature. Higher temperature, much faster recovery. Lower temperature, much longer recovery times. Transformation in materials over the course of time. What is happening at these grain boundaries and what diffusion is going on, how the diffusion is different, and what the degree of cooling, degree of supercooling, meaning delta T, bigger delta T or smaller delta T. Smaller delta T means slower. Larger delta T means faster. The faster you go, the faster you get down into another region, and how you go through these steps determines what kind of microstructure you have at the end. So most steels go through the austenite region and are cooled down below that in order to form something. Could be perlite and bainite together, could be spherodite if it's held at a very, very long time frame to completely equiax the grains. Quick and rapid thermal transition allows for a diffusionless crystallization process, forming martensite. And depending on what you're doing, martensite is extremely brittle, but you can temper it by bringing the temperature back up for a length of time. And adding some alloying elements can shift the nose of the curve slightly so that you have a little bit more time to be able to get quench going on. So there's annealing, and then there's all sorts of other things. So if you're cooling in a controlled manner, there's a couple different ways that you can control the grain structure and what the resultants are, what the approximate weight fractions are for different grain types, so that a material does a certain end performance. So perlite and spherodite and coarse perlite and fine perlite are all compared here in terms of hardness and ductility. Then there's other mechanical aspects, and tempered martensite becomes kind of one of the most important of the materials because you can control how they behave. So very high in strength, very low in ductility. Those have an inverse relationship, and depending on the cooling rate, you get different phases. So understanding how those different phases interact really is critical to all of the things in all of this. So when we go to alloy the metals, what happens, how these things are ranked. So we expect you to know about the steel naming schema so that you understand what's going on. So this is an important thing to study. Cast irons and behaviors within this iron phase diagram. Maybe we'll do copper, maybe we'll do something new and exciting like cobalt. You'll have to see when you get there. It'll be really exciting. So depending on what variety of cooling and what starting composition you have, you can get a lot of different types of iron with a lot of different properties. And there's also a lot of non-ferrous alloys because we sometimes need things that aren't extremely heavy and prone to corrosion. Sometimes we have other applications where something else is better. Maybe we need something that's non-reactive. Maybe we need something that's just lightweight. All of those parameters. So We use a lot of these in a lot of different applications, so it's important to know those. Important to understand the effects that these methods, forming, casting, and powder forming, where we're essentially doing metal injection molding with powders and then sintering them, meaning fusing the surface areas almost into new macroscopic grain boundaries. All of that, welding, etc., become really, really important. So thermal processing, what are annealing, normalizing, stress relief, you need to be able to clearly articulate all of these things because they all matter for the end application. So you have hardenable materials, and depending on how it's cooled, you see the differences in the hardness test of what these different cooling curves look like from martensite all the way out to perlite. And understanding what the geometry effects are of those things. Precipitation hardening, where we are including a heat treat and causing precipitates to form, doing the heat treat and such that we are aging the material in order to change its properties. Then we get to the polymers, which we've just gone over. So you need to understand fundamentals of processing, what these materials do, and how some of their behavior works, especially in regards to stress and strain and what this actually does. There's also the issues of corrosion and the electrochemical effects of these matters. So all of this is fair game for the test. A lot of different varieties and forms of corrosion. You can control things and have some sacrificial materials. So cathodic protection is a big deal. So we need to just have a clear understanding of what those things are. So there's a couple other lessons that you guys will need to go back and spend some time reviewing from the very, very beginning. But we need to bring this up for wrap so that you guys can actually go and study all of these things. Because there could be 10 million questions, and is this going to be on the test? Is that going to be on the test? You need to be familiar with all of the things that we've covered and learned for the semester. So that's of critical importance at this point. So that covers the majority of the chapters. You also want to make sure to go back and study the crystalline plane details, but ChatGPT did great on that first test, so I'm sure you'll all do fine, right? All right. That covers us for what we need to be focusing on. So it's kind of everything. So it's not just a list of like 6 things, because if you knew what you were being tested on and then you knew what the answers are, then you would be like a politician or something. So that's not how we do things. Yeah, I would say good luck, and may your results reflect the bounty of your studies.